We've considered the types of thinking that students can do in an inquiry-based approach to lab instruction. And it's these thinking processes that are really essential to the students' learning. We'll return to this idea in a minute, but first, let's take a minute and consider some different questions about an inquiry-based approach to labs. First, you may be wondering whether it's important that the questions that the students are asking are novel. As scientists, we're really trained to think that it's important that we ask novel questions and that we seek information that expands our knowledge base. Is it important in an inquiry-based lab for students to be doing just that? Well, the short answer is no. If we consider traditional labs, inquiry-based labs, and course-based undergraduate research on a continuum, students in traditional labs are never answering a novel question. They're always verifying known information. Students in a course-based undergraduate research experience, on the other hand, are always answering a novel question. Novelty is really an essential part of answering a research question in that type of approach. In inquiry-based labs, the questions that the students are answering are sometimes novel and sometimes have known answers. But what's really key is that the students don't know the answer, and they're designing an experiment to answer a question. They're not collecting data to verify a known truth. So in inquiry-based labs, the emphasis is really on the student learning rather than on gathering novel information. All right, so what sorts of benefits have been demonstrated for inquiry-based lab pedagogy? Well, there are really two types of benefits that have been demonstrated for inquiry-based labs. First, inquiry-based labs have been shown to lead to cognitive gains for students. That is, students have demonstrated increased content understanding and increased transferable skills like critical thinking, ability to design experiments, ability to analyze data. Secondly, inquiry-based labs have been shown to lead to affective gains, such as more positive attitudes about learning science and greater motivation for learning science. And these two types of benefits really get at what we want for our students. We want our students to love science, to love learning science, and to learn it really well in a way that they can use it later. And so an inquiry-based approach to lab instruction can help get our students where we really want them to be. Now, you may be wondering, does it always work? Sounds great. Are there any limitations to this approach? And of course there are. As with any teaching approach, implementation is really key. And with inquiry-based lab instruction, it's vital to include scaffolding and opportunities for practice to help students develop the needed thinking processes. What we're asking students to do in an inquiry-based lab is really challenging. We're asking them to evaluate different approaches to answering a question. We're asking them to synthesize observations to come up with a question and then, design a way to answer that question. These things are really quite challenging for students. And so if we don't include scaffolding and opportunities for students to practice these skills, then they don't necessarily achieve them. You'll notice that in the examples of inquiry-based labs that we looked at earlier, the astronomy lab example that Erica Grinstrom led, and the biological sciences example that Charles Sissom led, that there were multiple opportunities for students to practice and multiple types of support that were provided. Let's take a minute and consider some things that Erica and Charles have to say about how they provided this sort of support.
This is kind of a style that people have called backward faded scaffolding. So you provide a lot of support right away, and then you kind of gradually take away the supports over the course of one lab.
We had them as a checkpoint to how well they do in their experiments. We do a mid-semester presentation. The original goal was to do a pre-trial to kind of test proof of concept for the experiments they're designing. And the semester presentation is a reality check, as we call it, that, okay, now you must present your results. And for many students, it's the first time to also think about presenting publicly in a coherent fashion what they're doing, what they did, and how it relates to the real world.
So you'll note that Erica very consciously provided the sort of support that students needed to develop the skills for an inquiry-based lab using that backwards fated scaffolding approach that she described. Charles also very consciously provided support and structure for his students, helping point their research question in a particular direction, helping provide guidance for them as they developed that research question in their experimental plan, and incorporating an opportunity for them to do part of their project, get feedback from their peers and other instructors before then proceeding. So both Charles and Erica really illustrate how one can provide the sort of support that you need to make an inquiry-based approach to lab instruction successful.